So we're parameterizing a curve in terms of arc length. So it's kind of an interesting process. It boils down to, or at least it calls back to the fundamental theorem of calculus. So I'll just read the blurb here. Recall that there are infinitely many ways of parameterizing a curve. I mean, I say recall, it's kind of like a catch-all statement, but in order for you to recall, you'd have to remember something that I mentioned in passing like 2 months ago. So I don't know, if your memory's that good, then congratulations, you're going to go far. If not, then I can't blame you because I don't remember what I wore yesterday, let alone what I'm wearing today. A Harry Potter t-shirt. Let's keep the story home. Anyway, so you can parameterize a curve in a number of different ways. Right? What I'll do is I'll refresh your memory a little bit just by kind of off on the side here, just giving you a case. So let's say, for example, you have y equals x squared, something very simple. All right. The key to this whole thing when I parameterize is that I would have to decide what t is going to be equal to. All right. So I would let t be equal to something. And that's actually all I would need to do to justify that there's infinitely many ways to parameterize a curve. Yeah, so the question is, do we get a chance to resubmit the tech assignment B or update it before Wednesday? Yeah, totally. Yeah, you can always resubmit before the deadline. All right, so I'm going to let t be equal to 1/4 x. So, you could let it be whatever you want. Right? I could let it be equal to nx if I want, where I define some coefficient of x. It doesn't really make a difference. Right? In which case, I would say that x is equal to 4t. And then I would just do a quick substitution here. Since x is equal to 4t, I'd have y equal 4t squared, which if you wanted to actually square it out, would give you y equals 16t squared. All right, so that would be your set of parametrics that are consistent with y equals x squared. You graph them both, you get the same looking graph. It's just the rate at which you move along that graph would be different. All right, but that's not really the point behind all of this. The key to this whole thing, or at least that statement that I just made, where I say, recall there are infinitely many ways of parameterizing a curve, that has everything to do with that let statement that I just made arbitrarily. I said, let t equal 1/4 x. T could have been whatever I want. T could have been equal to the sine of x, right? T could be equal to the natural log of x, right? Maybe I want t to be something in terms of y. Or maybe a relationship between x and y if I want to get a little too crazy. But it could be anything. Right? When possible, it's often useful to parameterize a curve in terms of arc length so that each 1 unit increment in the parameter traces out exactly 1 unit of arc length on the curve. Right? So this is a little application of arc length. The idea is sometimes you don't want to know necessarily what your position is relative to some fixed point. If you go back to the graphs, it's been actually quite some time here. If you go back to the graphs on page 41, you see that each of these points is in reference to the origin, right? So when I talk about movement, like if I talk about a derivative or any kind of rate of change, it's the rate of change of the vectors, right? And the vectors the edges of those vectors happen to trace out the curve. But if I want my reference point to be a position that I previously achieved along that curve, then I would want to do it in terms of arc length, right? So I kind of look at it like you have, let's say, a mountain climber. And unfortunately for me, I watch way too much sci-fi, or fortunately, depending on your perspective of such things. The scene that comes to mind is one of the worst Star Trek movies out there, Star Trek V, The Final Frontier. There's a scene in there where Kirk is climbing El Capitan, the mountain, and I think it's Dr. McCoy is watching from a distance with a pair of binoculars. And so it doesn't have to be Star Trek. It could be anything, but the idea is that the fixed point would be the individual with the pair of binoculars watching the person progress along their path, right? The distance between me or that person with the binoculars and the person on the mountain, because I wouldn't be the one on the mountain, I'd be the one with the binoculars. The distance between those two individuals could be vector relationships, with the fixed point being the person with the binoculars. And then all the movements from that fixed point would be vector valued functions, tracing out the path of the individual climbing up the mountain, right? But if the frame of reference, so the person climbing the mountain, if his or her starting point is the frame of reference, then everything is with relation or with respect to a point along the path. All right. So that person started at the bottom of the mountain, and an hour later, he was X number of feet up. Then another hour later, he or she was X number of feet beyond that. All right. But it's always a point along the path. All right. So depending on the circumstances, you might care about both of those pieces of information. All right. Another quick example is a plane flying. You got the air traffic control, the control tower that's tracking all the movements of the planes. All right. There's a reason why they call it an approach vector, and so you have that, but then you also have the information from the perspective of the pilots, like where were we 5 minutes ago? Where are we now? All right. So those are positions along the path itself. All right. One is in relation to a fixed point on the ground. The other is in relation to the path of the object. All right. So those are some pretty significant applications of this concept. All right. So in order to parameterize, we need to get some kind of expression that represents arc length. All right. So to do this, recall that for the curve given by the vector value function, we can define an arc length by that lovely formula. The above integral relates arc length S to the given parameter t, which I'll walk you through in a minute. The idea is to evaluate the above integral to find S of t, invert the equation to obtain t of s, and then substitute t of s into the original parameterization to obtain arc length parameterization. All right. That's a mouthful. It doesn't really mean a whole heck of a lot without an example. So what I'll do is, well, first, I'm going to rewrite the model without all the fluff. We just kind of want to bring it down to brass tacks here. I'm going to call it S instead of S of t because we know it's going to be in terms of t. T sub 0 to t. All right. T, if we're assuming that represents time, we're talking kind of along the lines of how we defined a linear equation in terms of parametrics. We have a starting point, and then we have some variable point, some point that is allowed to vary depending on the passage of time. Right? R prime of u, or at least the magnitude of that, du. Right. So we have, and that's just to keep it general, really, more than anything else. We have our R of t. Our R of t function is in ij form, so I'm going to convert that over to component form. I would like to do that actually correctly, so hang on one sec. All right, so we have this R of t. We're going to need the derivative. All right. Now, according to this model here, it's supposed to be in terms of u, and I'll explain why that's the case in a minute. But the short reason or rationale behind that is we want to keep it in general terms. Right? So it's a quick and easy fix. All my t's get replaced with u's. Right? So that part shouldn't be a problem. Right? So I'm going to write r of u. I really don't need to write r of u, but I'm going to do it anyway, just for consistency. U squared u. And then r prime of u is equal to 2u comma 1. All right. So we're going to find the magnitude of the derivative of r with respect to u. All right. So what I'm going to do is I'm going to get a little sneaky here. And by sneaky, I mean incredibly lazy. I'm just going to pop some magnitudes around these bad boys. So that's going to be equal to the square root of 4u squared plus 1. All right. And so that's what we're going to be looking to integrate. I think I can tuck that off on the side. Tuck it off a little bit better than what I just did. That's fine. All right, so that's going to go in here. I can't make a radical anymore.
Professor?
You.
Why is that 4u squared plus 1 again? I'm sorry.
4u squared plus 1. When you find the magnitude, you square each part. Add them together.
Okay. Yeah. Thank you.
No problem. Moving this over a little bit. So this is what we have to integrate. So once we integrate this, we'll have a relationship between S and T. It's just a question of what that relationship is going to be. And that part is okay. All right. Now, in terms of the lower and upper bounds, we're going from 0 to, we're going from T0 to T. Now, I stole my own thunder there a little bit, because in going from T0 to T, we're really looking at some fixed value and some variable quantity, right? So it's really just a question of where you want to start this journey, right? So what we do is we establish that the lower bound has to be some constant, right? So T0 has to be a constant. I'll make a note of that. So without any other information, what we do is we let that be equal to 0. Unless you have a better value, you know, and you could kind of let the integration play itself out before you really kind of decide. But essentially, it really is just a matter of saying, well, I think this makes most sense, so let's go from it, you know. So maybe it makes more sense to let it be equal to 1/2 or like 7 or something like that. But without any kind of information, we'll just say 0 and then we'll play it from there. Right? So, but we do have to integrate it. If I can get a sentence out without coughing, or at least having to clear my throat. So it's a question of, okay, now what technique is going to be most appropriate for integrating this? Now, we have tackled this kind of problem before. That doesn't mean that it's an easy one, and it doesn't mean it's something that you're going to want to do, but we can integrate this. It just requires us to use trig substitution. Okay. So really just kind of setting up the triangle that makes all the difference here. All right. So, and kind of seeing here that space on this problem probably a little bit of an issue. So I'll take it as a typo from somebody. So okay. If I let the opposite side be equal to 2u, the adjacent side be equal to 1, opposite over adjacent would be tangent, is equal to 2u. And then hypotenuse over adjacent, which is secant, would be the radical. All right, so we just have to clean this up a little bit. So u would be equal to 1/2 tangent theta, the derivative of which is going to be du equals 1/2 secant squared theta d theta. All right, so we can perform our substitution. Like I said, not pretty, but definitely doable. Right? The issue here is that we're kind of stuck with a little bit of Calc 2 content, because it's non-numerical in terms of the bounds. If it was numerical, I'd say pop it into your calculator, be done with it. But that's unfortunately not the case. Right? But we can get through it. S equals, and like I said, I'm going to let the low bound be equal to 0, unless I have reason to think otherwise. Secant is going to swap out the radical. We'll highlight that in green. And du is going to get replaced by 1/2 secant squared theta d theta. That should be the typo coming in. Because the more I write, the more you realize that there just isn't enough room for this question. Or for this solution. So then we have secant cubed, and like we definitely did this problem before. I actually remember it because that was the night I broke, the night I broke into the coughing fit and I had to excuse myself. That night I bought like a lifetime supply of cough drops, and then ran out of those like last week. So it really wasn't a lifetime supply. But what I can do is, just for the sake of brevity here, take us right on back to the scene of the crime, wherever that is. Should be back a long, long way. And steal that work. Yeah, it's the one with like a ton of work. So the secant cubed, just so, again, so I don't have to rewrite all this stuff. Secant cubed ended up being this lovely Oh, actually, that was after a substitution. Yeah, so we don't even want that lovely. We want this lovely. All right, so that's what that secant cubed is going to be equivalent to. And then we're just evaluating that for when t is equal to, or I'm sorry, when the lower and upper bounds are what they are. But we do have to do some reverse substituting to get it in the appropriate form, right? Unless we want to create bounds in terms of t. That's perfectly fine too. You know, so if I create my, instead of having bounds in terms of u bounds in terms of t, I could have theta bounds in terms of something else, right? So actually, these bounds aren't really appropriate now that I have them here. I should get rid of those because we're going boundless at this point. But I can just do the quick substitution, the reverse of this, the reverse substituting. So I just grab a nice little relationship in terms of u that would allow me to swap out all of my my thetas. So I would just make a little note here that, and I'll use this Jimmy Jammy right here. That theta is equal to the inverse tangent of 2u. So then all of my thetas can be replaced with this expression, which doesn't really sound like it's going to do much, but it's actually going to do a fairly great deal. Right? So let me just get that going here. So we're looking at 1/2 secant of tangent to inverse tangent to u. Then we're going to have tangent of inverse tangent of 2u. Right, that's the first nice thing that's happened all class. So tangent of inverse tangent of 2u is just going to become a 2u. So I'm just going to pop in a times 2u. Plus 1/2 ln of secant of the inverse tangent of 2u. Plus tangent of the inverse tangent of 2u, which is another plus 2u. All right. Do a little bit more housekeeping. It just doesn't seem like it's going to go in a place that's going to be overly useful, but it is going to clean up so that we get rid of all the trig. And then once we do that, then we can evaluate for the given bounds. But that part is going to be the easiest part. All right. Well, I'll say the only easy part. So the secant of the inverse tangent of 2u, secant theta, if you want. I mean, that's really the triangle, and it's really the secant ratio. And in fact, if you look over here, let me highlight that. Well, I think I've highlighted enough. We already have a relationship for the secant of theta. So that can just get swapped out for 1/2 the radical 4u squared plus 1. So I'm going to have the 2 going with the 2. So u radical 4u squared plus 1 plus, still got the 1/2 for the ln, radical 4u squared plus 1 plus a 2u. All right, so that is getting evaluated over the interval of some low bound for tu, some constant low bound up to just a t. So what we would do is just make sure that the low bound that we decided on of 0 is going to make sense for this situation. Right? And it looks like it will. I mean, it's not going to be any prettier, because 0 usually ends up being a nice, like, okay, we can cancel a lot of stuff out situation, but not the case here. Right? We're going to get stuck with some terms, but that's okay. Right? So I'm going to get all of this stuff again, just with the T. So let me just do a copy. So every U gets replaced with a T. Then when I subtract off the substituting of 0 in, the first part is going to cancel away. That's fine. But then I'm going to get stuck with the second piece, which mostly is going to cancel away. But you're going to get a 1/2 ln, as it turns out, of 1, which fortunately ends up being equal to 0, but there was no guarantee until we dove into it. So we got to be careful. So we actually lucked out here that it ended up going to 0, but you can't make that assumption going in. All right. So all of this would be equal to S. And so that would give us a parameterization for S in terms of T. So we now have a clean, well, clean is the operative term here. We have a relationship between S and T. It's just not a nice one, right? But solving this equation, so all of this stuff, solving this for T in terms of S. So we have S in terms of T. Solving this for T in terms of S would allow us to swap out any variable that exists within the function, right? And make it R of S instead of R of T. But this is a mess. So obviously it's not something that people are keen on doing, but that's the gist of how you go about doing it. I got to shrink this down a lot in order to make it try to fit. Let's see if I can get this in over here somewhere. All right, so all we're doing here is we're looking for a relationship between S and T. If we could find that relationship, then everything tends to work itself out. All right, easier said than done in some cases. Right? This is definitely a case where it's easier said than done. So I'll take you through a couple of cases where it actually works out kind of nicely, and then you can kind of get the idea of what a good, clean looking example looks like. All right, so number 5 is find the arc length parameterization for a circle of radius 2, traced out by the BVF that you see there on the given domain. All right, so it's the same initial setup. The integration part of it is going to go a lot smoother. So that part is going to be okay. It's just it just doesn't seem like it would. Right? And as you hopefully have recognized by now, I prefer the component form of vectors, and I think a lot of people do. But I think just as many people prefer the IJK notation. So it's up to you how you want to do it. But cosine 2 cosine t to sine t. All right, so that's the equation of a circle. R prime. It's going to be -2 sine t, and then 2 cosine t. All right. Then replace it with u's. And for now, all I have for you, or all I've offered in terms of an explanation for why we're changing it to U, is because that's what the formula says. But there is a better reason for that, and we're getting there. So just sit tight on that one. We need the magnitude. And this is really where all the magic happens. And also it's the payoff for studying your unit circle stuff. So, or at least your trig relationships. The -2 sine U is getting squared, and so is 2 cosine U. So we're looking at 4 sine squared plus 4 cosine squared. Okay. Now we have a GCF here of 4 that can be pulled out of the whole thing, or you can just pull it out on the inside and not factor it out of the radical. It really doesn't make a difference the way it's going to play out. And that's because sine squared U plus cosine squared U is a Pythagorean identity, which is equal to 1. So that's going to cancel away. All right, that's why we like the trig ones. All right, they clean up kind of nicely. Right, so we have the square root of 4, which is just a 2. All right. Now, if we're looking at the magnitude of the rate of change of a function, I mean, that's a little wishy-washy in terms of what its meaning could be, at least at this point. But if I ask you to find the magnitude of just r of t, and we know it's a circle, that magnitude is going to be represented by the radius, right? Since the derivative of a circle in vector valued form is another circle, it's just its movement around that circle is different, then its radius will still dictate what the magnitude is. So there's a little bit of a built-in shortcut when it comes to conic sections. Right? So in the past, you kind of dreaded those things. Now you find yourself looking forward to them rather than the polynomial stuff. Right? It's kind of like why I led with the nasty one, where it's like, like if your next step here in number 4 was to say, okay, now I got to solve for t, you look at that for a while and be like, I don't even know how to do that. But here, it's going to work out a lot nicer because my integral, so again, S, going from some unknown but constant value on the low end to t, right, variable t. Now, it's just 2 du. I don't need to do any fancy trig there because the antiderivative of a constant, that's simple. You just slap on a u and call it a day, right? So we're looking at S equals 2u on the interval of t sub 0 to t. But again, we have the option to choose where we want to start our t. That goes all the way back to what I said above. I can let t be equal to whatever I want. All right. Now, on a variable note, I want to keep it variable, but on a constant note, I'd like to let that be equal to 0. Right? If I have a choice, I'm going to let it be the simplest value that it can be. Right? So we'd have S equals 2t. Right? And minus 2 times 0, but still. I mean, that's as nice as it gets. So number 4 was as ugly as it gets. This is as nice as it gets. Here we could actually do something with it, right? Because I look at this and I say, all right, well, I know that S is equal to 2t. That tells me by extension, or consequently, t would be equal to 1/2 S. So a parameterization would be, instead of writing my vector value function in terms of t, I'd write it in terms of s. I now know that t is equivalent to 1/2 s based off of this relationship. So in my r of t, which again, I like the component form, I can swap out all of my t's, or each of my t's, for a 1/2 s. Well, actually, this one should just be r of s. Here it's going to be t becomes 1/2 s. The reason why it's r of s on the left is because it's still going to be a function r in terms of s. It's just in what capacity it's of s. That's what's dictated on the right-hand side. And then if you wanted to clean that up with some half angle identities, I would caution you and say, you only might think you're cleaning it up. They're actually going to make it a lot worse. So you're better off just leaving it like this. Same thing with double angle relationships. Almost always you're better off just leaving it as like cosine 2s, sine of 2s, than it is to expand it out. It makes matters worse. All right. So this is what r of s would be parameterized in terms of s. All right. Now, the good news is, building off of number 5, we could either do all of that stuff again, just with coefficients of a, or we could learn from what we just did, right? And so for number 6, it really is just kind of looking at these two pieces of information and saying, okay, well, where'd that 2 come from? That 2 in the relationship came from the radius. So if I did all this again, just with a coefficient of a, it would become 1 over as, or you could write it as s over a. In which case we would get, without doing any of that work, a parameterization in terms of s. All right. But we did the work, we just did it and referred to it rather than doing it and doing it again. It's a time saver. All right. Now, number 7, I always get to this one and I say, I don't want to do it. I'm sure we'll all get over it very quickly and easily if I skip it, but that's where the guilt comes in. Now, maybe I'll come back to it at some point. It's just, it's beating a dead horse. That's really all it is. Because when you graph a circular helix, and that's what this one is, because it's given a radius r, you have, well, I'll give you the r of t, and if you want, you can kind of play around with it, but you have r of t would have the components of r cosine t, r sine t, and then t. So you get an extra layer that you have to deal with, and that is the third dimension. So in terms of your setup, oh, now I feel obligated. I'm going to do it. So r prime of t would be equal to negative r sine t, r cosine t, comma 1. Right, replacing that with a set of u's and coming up with the magnitude. We're just squaring each part, replacing all the t's with u's and adding it together. All right, so negative r sine u squared plus r cosine u squared plus 1 squared. And then after this is where things get a little tangy. Because you can clean it up, but the trig knowledge is going to have to work its way in here at some point. All right, so we're going to have r squared sine squared. R squared cosine squared plus 1. You have the GCF of r squared. Which cancels to a 1, but you're still stuck with that r squared plus 1 on the bottom. Right? And so then this problem becomes a whole lot more like number 4 than like numbers 5 and 6. Right? So you'd be looking at now, or at least at first glance, I'll show you what I mean by that. Appearances can be deceiving. Right? So we would have S equal to T sub O to T. You'd have the R squared plus 1 and du. All right. So appearance-wise, it looks like I said, more like number 4 than numbers 5 or 6. But the one thing that you might take note of is the fact that any trace of a u has disappeared. Right. So while it might look like a trig substitution type situation, this whole shibiggity bangity boom here is constant. And dictated based off of whatever r is equal to. All right. So my integral is going to be all of that multiplied by u. So a radical r squared plus 1, and that whole thing would then be multiplied by a u. And like I said before, if you have a choice in a matter, why not let that be equal to 0? Because you do have a choice in the matter. So 0 to t, which in turn would give you t root r squared plus 1. So that's what S is equal to. Right? Because you plug in a 0, zaps away, so we're not worried about that. Right? But that allows us to solve and parameterize in terms of S. So I can solve for t. T would be equal to S over the square root of r squared plus 1. And so all I would have to do is replace all of my t's with that expression, and we would have a new parameterization, specifically r of S. So I'm just going to bring it in, clean it up. So every t goes away, is replaced with an S, with an expression involving an S. A little bit more room here. Drop it in this. Undo, kill this guy. And then just to make it look somewhat decent, somewhat, slap some parentheses in here. All right, so that's what the R of S parameterization would look like for this problem. All right, so started off by saying I wasn't going to do it, and I figured I would just get it started, and then I couldn't stop myself. So here we are. It's a good problem, though. It's a fun problem. The only one really that isn't fun is number 4, but it's only not fun because you don't get to a final conclusion, or at least not easily. I mean, you need another page of work ahead of you before you can get there. Because you got to convert it over into exponential form. It's not pretty. All right, so we're gonna hop on over to page 48. Let me stop this video.